The algebra of sets defines the properties and laws of sets, the set-theoretic operations of union, intersection, and complementation, and the relations of set equality and set inclusion. It also provides systematic procedures for evaluating expressions, and performing calculations, involving these operations and relations. Any set of sets closed under the set-theoretic operations forms a Boolean algebra, with the join operator being union, the meet operator being intersection, and the complement operator being set complement. Fundamentals. The algebra of sets is the set-theoretic analog of the algebra of numbers. Just as arithmetic addition and multiplication are associative and commutative, so are set union and intersection. Just as the arithmetic relation, less than or equal, is reflexive, antisymmetric and transitive, so is the set relation of subset. It is the algebra of the set-theoretic operations of union, intersection and complementation, and the relations of equality and inclusion. For a basic introduction to sets, see the article on sets. For a fuller account, see naive set theory. And for a full rigorous axiomatic treatment, see axiomatic set theory. The fundamental laws of set algebra. The binary operations of set union satisfy many identities. Several of these identities or laws have well-established names: commutative laws, associative laws, distributive laws. The analogy between unions and intersections of sets, and addition and multiplication of numbers, is quite striking. However, unlike addition and multiplication, union also distributes over intersection. Two additional pairs of laws involve the special sets called the empty set O and the universal set, together with the complement operator. The empty set has no members, and the universal set has all possible members. Identity laws. Complement laws. The identity laws say that, just like 0 and 1 for addition and multiplication, O and U are the identity elements for union and intersection, respectively. Unlike addition and multiplication, union and intersection do not have inverse elements. However, the complement laws give the fundamental properties of the somewhat inverse-like unary operation of set complementation. The preceding 5 pairs of laws, the commutative, associative, distributive, identity and complement laws, encompass all of set algebra, in the sense that every valid proposition in the algebra of sets can be derived from them. Note that if the complement laws are weakened to the rule, then this is exactly the algebra of propositional linear logic. The principle of duality. Each of the identities stated above is one of a pair of identities such that each can be transformed into the other by interchanging in, and also O and U. These are examples of an extremely important and powerful property of set algebra, namely, the principle of duality for sets, which asserts that for any true statement about sets, the dual statement obtained by interchanging unions and intersections, interchanging U and O and reversing inclusions, is also true. A statement is said to be self-dual if it is equal to its own dual. Some additional laws for unions and intersections. The following proposition states 6 more important laws of set algebra, involving unions and intersections. Proposition 3. For any subsets A and B of a universal set U, the following identities hold: idempotent laws, domination laws, absorption laws. As noted above, each of the laws stated in Proposition 3 can be derived from the 5 fundamental pairs of laws stated above. As an illustration, a proof is given below for the idempotent law for union. Proof. The following proof illustrates that the dual of the above proof is the proof of the dual of the idempotent law for union, namely the idempotent law for intersection. Proof. Intersection can be expressed in terms of set difference. Some additional laws for complements. The following proposition states 5 more important laws of set algebra, involving complements. Proposition 4. Let A and B be subsets of a universe U, then. De Morgan's laws. Double complement or involution law. Complement laws for the universal set and the empty set. Notice that the double complement law is self-dual. The next proposition, which is also self-dual, says that the complement of a set is the only set that satisfies the complement laws. In other words, complementation is characterized by the complement laws. Proposition 5. Let A and B be subsets of a universe U, then. Uniqueness of complements. If, and, then. The algebra of inclusion. The following proposition says that inclusion, that is the binary relation of one set being a subset of another, is a partial order. Proposition 6. If A, B and C are sets, then the following hold: reflexivity, antisymmetry, and if and only if, transitivity. If and then. The following proposition says that for any set S, the power set of S, ordered by inclusion, is a bounded lattice, and hence together with the distributive and complement laws above, show that it is a Boolean algebra. Proposition 7. If A, B and C are subsets of a set S, then the following hold: existence of a least element and a greatest element. Existence adjoins. If and then. Existence of meets. If and then. The following proposition says that the statement is equivalent to various other statements involving unions, intersections and complements. Proposition 8. For any two sets A and B, the following are equivalent. The above proposition shows that the relation of set inclusion can be characterized by either of the operations of set union or set intersection, which means that the notion of set inclusion is axiomatically superfluous. The algebra of relative complements. The following proposition lists several identities concerning relative complements and set-theoretic differences. Proposition 9. For any universe U and subsets A, B, and C of U, the following identities hold.